Okay, during the last video we spoke about how you can have quantitative and qualitative measurements, and we discussed the difference between them. And then we also looked at how you can put numbers in and out of scientific notation. And now we've practiced that skill and really discussed what it means to be quantitative versus qualitative. One of the really important things about being quantitative are units. Units are the tags that you attach to numbers. And so you could have a quantity, like mass for example, but if you don't put a unit to it, it doesn't mean as much as it could. So for example, if I were to say that somebody weighed 100, you wouldn't really know what that meant unless you put a tag on it, like you said, well, they weigh 100 pounds, or they weigh 100 kilograms. Well, there's a difference between them. Now, when we look at units of measurement, we try to use ones that are used internationally, ones that every scientist can understand. And unfortunately, the units that we use in the United States are often different than what is used internationally. Like when we do a mass, we talk about kilograms, length, meters, time, seconds. In the United States, when we talk about length, we often talk about miles or feet, and these are not considered international units. Later on in the slide presentation, you'll see that there's a conversion between meters and miles, meters and feet. And so it's important that you be able to do those conversions. We'll go through specifically how you would actually do that. So here are some what they call base units. And these base units, they are fundamental. They can't be broken down anymore. So if I'm measuring temperature, for example, temperature is measured in Kelvin, time in seconds, length in meters. I can't get any lower than that. So that's why they're called base units. We can use these base units to build other units. So these are sort of like our building blocks for other units. And they're really fundamental, meaning that they can't be broken down to anything less than what they are there. Now, we're going to do a lot of combining units together. You know, a commonly combined unit that we would do would be something like density. Density you've studied a whole bunch of times. You've seen this in 7th grade. You've seen this probably in earth science. And density is conceptually, you know, how much volume something takes up based on its mass. But mathematically, when we look at it, it's mass over volume. And we'll get more into density and the units of what they mean. So we'll come back and we'll look more closely at density and what a typical mass and a typical volume is when we're measuring density for different types of substances. But when we look at density, one of the units is volume. And volume is actually a derived unit where you have a length times a width times a height. And so this creates a situation where you have a cubic unit. Like if we look, for example, at the first square here that I have, first cube, I have a length 1 meter by a width 1 meter by a height 1 meter, and that gives me a cubic unit, meter cubed. Now what I've done is I've divided up each of those 1 meters into 10 blocks. And so we can see there's 10 blocks here, and those 10 blocks, each one of them is smaller. Each one of them is a decimeter. And so if I take this decimeter out and I enlarge it, then I will have a new block that is 1/10 the size on each length. So I will have, for each dimension, I will have 1 decimeter, 1 decimeter, 1 decimeter. And so if we think about this first one, each length is 1 times 1 times 1, and they're all meters. Well, we would have 1 meter cubed, and that's what we have down here. When we look at the next cube, each one is 1 decimeter, which is 1/10 of a meter. So we have 1/10 times 1/10 times 1/10. So this is 1,000th of a meter cubed. Now, it's also 1 decimeter. So this is 1 decimeter times 1 decimeter times 1 decimeter. And so this is also 1 decimeter cubed, which we call a liter. Please memorize that conversion. 1 decimeter cubed is 1 liter. Now we could take just 1/10 of a decimeter, which is a centimeter, and we would have 1 centimeter by 1 centimeter by 1 centimeter. Now if we look at that in terms of meters, then we have a centimeter is 1/100th of a centimeter, and each one of them is 1/100th of a centimeter. And so we'll actually have, instead of 1,000, we'll have 1/1,000,000th, 10 to the 6th, of a meter cubed. But since it's all this should be 1 meter, just to correct this. 1 meter, 1 meter, 1 meter, not 1 centimeter. So this would be 1/1,000,000th of a meter. If we did it in centimeters, which I'll do down here, it would be 1 centimeter times 1 centimeter times 1 centimeter, and that would be 1 centimeter cubed. So look at what happens though. We started off with 1 meter. We changed the length to 1/10. Look at what happened to the volume. It became 1,000th of what it was. Then we changed the length again by 10, which is really 100th of a meter. And now the volume went to 1/1,000,000th of a meter cubed. So my advice to you is when you look at volumes, and when you look at any units, and we're going to come back to this again and again and again, when you change the dimension by 10, the volume changes by 1,000. And you can see that because what we do is we normally don't deal with the cubic part. We deal with liters, milliliters, and a meter cubed is actually called a kiloliter. And so we have these 3 units, kiloliter, liter, milliliter, and they are all 1,000th of each other, even though the dimensions that make them up are only 1/10. Now when we do conversions and we have cubic units, you're going to have to cube the conversion factors. You're going to see that. Now let's look at a derived unit density. So, most of you know density is equal to mass over volume. And I can have different substances, like a gas, for example, air, which is a mixture of different gases. The density of air is about 1.28 grams for every 1 liter. So imagine a small seltzer bottle. That's about 1 liter. Inside there, if I were to fill it with air, it would be 1.28 grams. It would basically be very, very light because there wouldn't be a lot of air in there. Take, for example, though, if I were to do water. Now, water, the density of water at room temperature is about 1 gram for every 1 milliliter. Or, and I'll show you how to do these conversions later on, this is 1,000 grams for every 1 liter. So look at the comparison here. When I have water, which is a liquid, the density has gone up significantly. There are some solids that are really, really dense. So I would have, for example, let's say gold. Gold has a density of 19.3 grams for every 1 milliliter. Well, look at what that density is. That's 19,300 grams for every 1 liter. So if I were to give you, for example, a piece of solid gold, and then ask you to say, okay, well, what is how much would this 1 liter gold weigh? It would weigh 19,300 grams. That's a lot. If we were to change that into pounds, you would divide that by about 500. So if you divide it by around 500, you would get the number of pounds that is. So if we do that really quickly, 19,300 divided by 500, so we cross out those zeros, and we have about 200 divided by 4. That would be about a 40-pound. That would be about a 40-pound bottle of seltzer, 1 liter. Imagine that. That's pretty crazy. If we were to do that here with water, that same bottle of water filled with just water, or same bottle of seltzer filled with just water, would be 1,000 divided by 500, and that would give you about 2 pounds. And the air, well, you wouldn't even bother changing it to pounds. It would be so small. So wow, look at the difference here. Density makes up a huge difference. When we think about density, it's the mass per volume. The more dense something is, when we think about density, the more dense it is. That means that the same volume has more mass. And that more mass is generally due to packing of particles. How closely are they packed together? Are they packed far apart, or are they packed close together? Well, the more dense you are, the closer the packing. So more dense equals more closely packed. This may seem like common sense to you, but a few years ago they had a Regents question like this, and they wanted you to really, break it apart and state the packing of particles and how it affected density. Now there's another unit that we use, which I want to go into before we end the video, and that's specific gravity. And specific gravity, basically it's like a sink or float type of unit. What we do for specific gravity is we say that specific gravity is equal to the density of the object, whatever it is, divided by the density of a standard. Generally, this standard is water. So let's say, for example, I took gold and I had, 19.3 grams per centimeter cubed. That's my gold density. And I compare it to the water standard. The water standard is 1 gram per centimeter cubed. Well, look at what happens. It's just the same number, 19.3. But now there's no units. Specific gravity is just density without the units. But something that's important about specific gravity is that the comparison between your object and your standard need the same units. So you can't go ahead and have a situation where you put your density of your object in grams per liter, or grams per milliliter, grams per decimeter cubed, and your water is in grams per centimeter cubed. It won't work. The units have to be the same. Okay? They need the same units. So what we've done so far is we've spoken about, specific SI units. And just to scroll back here, the specific SI units that we talked about were mass, length, time, temperature. There's this unit that we haven't gotten into, amount of substance, called a mole. We're going to do a lot with moles. We called them base units. And then we also talked about how you can combine them to make a derived unit. One derived unit is volume. But there are other derived units such as density. And we can also use specific gravity. basically telling you if an object sinks or floats. So when I look at gold's density, it's 19.3. Its specific gravity is also 19.3. Since the specific gravity is greater than the density of the standard, what ends up happening is the object will float, the object will sink, sorry. If the specific gravity was less than the standard, the object would float. Now, what we're going to do next is talk about prefixes. And honestly, I don't expect you to memorize all of these, but a lot of them I expect you to know, like kilo, deci, centi, milli, micro, nano, pico. Those are the ones that I really focus on. Now, we're going to go in the next video into this in more detail. I'm going to stop for now here, and we'll pick up with prefixes.